All right, let's see if I can get this. It's probably better. All right, so little update on lemons. So evidently, like a main power cord to lemons died, like the main power cord going into the building. And PGE, I don't know if everybody knows this, but there's been like all sorts of power outages around Oregon. So PGE is like a little bit busy, like restoring people's power. So that just hasn't been a big priority. And so supposedly they'll be here on Wednesday to replace the cord. So probably we won't have class in there on Wednesday. Maybe we'll do here again on Wednesday. And then Friday we should be back in Lemons. So that's kind of where it's at on our classroom. So today we are going to start a new section. So section 26. And the section is on the mean value. All right, so the mean value theorem is kind of the big event of this section, but there are a lot of other little theorems that come with the mean value theorem that are important theorems. So we'll cover a bunch of different theorems in this section that are kind of cool calculus theorems. So let's start with theorem. This is theorem 26.1, which says if f is differentiable on an open interval AB, and if f assumes its maximum or minimum at a point C in AB, then we have that f prime of C is 0. Okay, so basically what this says is that if you're a differentiable function over an open interval, if you have a max or min, then the derivative at that max or min is 0. And if you remember from calculus, what is this kind of saying? So remember, we won't really talk about this in the same way that we would have in Calculus 1. But in Calculus 1, when you start learning about derivatives, you learn about things that are called like critical points or critical values. And critical points or critical values are typically places where the derivative is 0. And we're able to kind of search for max and mins using the critical points because of this theorem, because we know that at all those critical points, the derivative is 0. So if we know all the places where the derivative is 0, then some of those places must be the maximums or the minimums, right? But this is the theorem that gives us that all the maximums and minimums on an open interval are going to be at places where the derivative is 0. So let's prove this. So proof. So without loss of generality, assume f attains its maximum value at some point C inside of AB. And though without loss of generality, as I'm saying, let's just say it hits a maximum. It could be a minimum, but the argument is very much the same. Okay, so what it means to be a maximum value is that f of x is less than or equal to f of c for all x in AB. For all x in AB. Okay, so what I'm going to do is now I'm going to look at a sequence inside of AB that approaches this value C from different sides. And we'll see why in just a second. So, so let's let the sequence x sub n be a sequence in AB such that A is less than x sub n is less than C for all in the naturals. So what I'm doing is C lives between A and B somewhere. And what I'm saying is let's take my sequence of values. I can take any sequence I want to. I want to take the sequence so that all the sequence values come before C. Okay. Also, I would I also would like, did I say this? Also, we want these x sub n's to converge to C. So I'm taking a bunch of sequence values that are to the left of C that converge to C. Okay. If that's the case, then tell me something about the following. F of x sub n minus f of C. So tell me, is this value right here a positive value or a negative value?
Negative.
Why negative?
F of C is the max.
Yeah, f of C is the biggest that f can ever get on the interval, right? So this guy must be smaller than this guy because that's the maximum. So this must be negative. Could it be equal?
If there's more than one max.
Yeah, so it could technically be equal because I don't know that that's the only place that there's a maximum. So it could be equal to 0 as well. Okay, very good. And tell me about this one. What about x in minus C? Is this positive, negative, 0? What do we think?
That's also negative.
Yeah, we know that x in is less than C, right? Even strictly less than C. So we could say that this one is strictly less than 0. So in other words, this value right here is negative or 0. This one is certainly negative. So what if we looked at the following? So what if we looked at f of x sub n minus f of C over x sub n minus C? What do you think of that one?
Positive or 0.
Positive or 0, because both of these are less than or equal to 0. So this one must be greater than or equal to 0 for all in. So that would tell me that f prime of C, which is equal to the limit, you could say, as n goes to infinity of this difference quotient, f of x in minus f of c over x sub n minus c. So if I take the limit of a sequence that's all non-negative, what do we know about the limit itself? It's non-negative, right? It can't end up having a limit that's negative. So this thing has to be greater than or equal to 0. And I believe that's theorem 25. Let's see. Theorem 25.3. Okay. Now, let's look at another sequence. Okay, so basically what I just said is that the derivative at c is greater than or equal to 0, correct? So now what I'm going to do is I'm going to do the same argument. Remember here I started with a sequence that was to the left of c. Now let's take a sequence that's to the right of c and do the exact same process. So I'll say now let, let's call it y sub n be a sequence such that we have c less than y sub n is less than b. So now the y sub n's are to the right of c. So in a similar way, we can start looking at these where the y sub n's converge to c. Okay, so now let's look at f y sub n minus f of c. What can we say about this one? Positive, negative, 0. What do you think? Greater than or equal to?
That's still less than because after c is the max.
Yeah, this guy's still the max, so that's bigger than everybody else, or equal to, right? So this one will be less than or equal to 0, right? And let's look at y sub n minus c. What about that one?
That one's different.
Yeah, that one is different. What is it?
It's positive.
Yeah, it has to be strictly positive. So that means that f of y sub n minus f of c over y sub n minus c is what?
Negative. Of course.
Yeah, it's going to be less than or equal to 0, right? So that means that f prime at c, which is the limit as n goes to infinity of f of y sub n minus f of c over y sub n minus c, has to be less than or equal to 0. So what I just got is that f prime of c is less than or equal to 0. Over here I have that f prime of c is greater than or equal to 0. And so I can conclude that, therefore, f prime of c is 0 if c is a max on the open interval from A to B. And we're done. And I said with that loss of generality, the exact same argument could be made for a minimum. Any questions? So that's kind of a nice result. We basically now know that if you have a max or a min, then, and you know it's differentiable there, then it has to have a derivative at 0, right? There are things that kind of make you question, and it's kind of like, okay, well, something like that, that doesn't have a derivative of 0 up at this point, right? But what would you say? It's not differentiable. That's right. So it's kind of like if it is differentiable and it is a max or a min, then its derivative has to be 0. If it's not differentiable, then, well, all bets are off. Okay. All right. Our next theorem is theorem 26.2. Which is called Rolle's theorem. Okay, let me write it down. So Rolle's theorem says, let f be a continuous function on closed interval AB that is differentiable on the open interval AB and such that f of A is the same thing as f of B. Then there exists a point C in AB such that f prime of C is 0. Okay. Did any of you actually take Calculus 1 from me? You did?
Yeah.
And no one else? Okay. Did I make you learn this theorem?
Yeah, this one like 3 others.
Yeah. And the 3 others we'll probably do either today or next time.
Yeah,
in
mean
class.
value theorem was one of them.
Yeah, the mean value theorem was one of them. Yeah, so one of the things I do when I teach Calculus 1 is in the section on the mean value theorem, there's 4 kind of important theorems in that section. And I actually make my calculus students learn those 4 theorems just to get a taste of like what like real math is all about. And so this is the first one that I have them learn is Rolle's theorem. All of these are sort of understandable proofs for an undergrad. But before I prove this, let's just take a look at it and kind of see what it's saying. And what it says is if you have your axis and you have a point A, you have a point B, and f of A and f of B are the same thing, then somewhere in between, given that the function is continuous on AB and differentiable on the open interval from A to B, then somewhere in between the derivative needs to be 0. So there's actually kind of 2 things that could happen here, and we have to think about both of them. The first one is kind of simple, and that is, well, what if it was just a straight line? If it's just a straight line or it's a constant function, then is there somewhere in between where the derivative is 0?
Everything.
Yeah, all of the places, right? So a constant function has derivative 0. So all of the places would have derivative 0, and that seems fine. Then the other situation that could happen is, again, the endpoints have to be equal, is that this thing is not constant. But if it's not constant, then these 2 points can't be both the max and the min, right? So they could be one, right? Like it could just go up and then down, right? So these could be the minimum values, but they can't be the maximum and the minimum values. The only way it could be that is if it's a constant function. Yeah.
Couldn't they also be neither?
They could be neither. That's right. But all that I need for sure is that they're not one of them. Okay, but yeah, you're totally right. You could have a situation where like you have something like this, right? Where they're the endpoints aren't the min or the max. But it's good enough for me if I just know they're not both. So in this case, they're actually both, right? They're the max and the mins. But as soon as you say they're not both, then somewhere in between is a max or a min. And as soon as somewhere in between is a max or a min at a differentiable point on open interval AB, we just proved that its derivative is 0. And we're done. So that's the whole proof basically in a nutshell, but we should probably still write it down. Okay. All right, so proof. So F is continuous and the closed interval from A to B is compact. So corollary 22.3 implies that there exists x sub 1 and x2 in AB such that f of x1 is less than or equal to f of x is less than or equal to f of x sub 2 for all x in the closed interval AB. Okay, so in other words, on a compact, continuous function on a compact interval guarantees me a maximum value and a minimum value on that compact interval, right? That's not true on an open interval, by the way, just as a reminder. But since we're on a compact interval, I'm guaranteed to have a maximum value and a minimum value. Okay. If x1 and x2 are the endpoints A and B, then we have the following. That f of A is less than or equal to f of x is less than or equal to f of B, which is equal to f of A, because that's what was given to us in the problem, that f of A and f of B are the same. So that means that f of A is less than or equal to any value f of x is less than or equal to f of A for all x in the closed interval from A to B. But that's basically, I mean, not basically, it is the definition of being constant, is everything equals f of A. So f of x is equal to f of A for all x in AB. So f of x is constant. So that means that f prime of x is equal to 0 for all x in the open interval from A to B, and we are done. Okay, so argument number 1 is A and B are the max and the min, which means that all the values fall in between f of A and f of B, which is f of A. So all the values fall within f of A and f of A. So they are all f of A. So it's a constant function. And we know that a constant function's derivative is 0 everywhere. So we're done. That means there is somewhere in between A and B where the derivative is 0. All of the places. Okay, that's kind of the easy case. The second case is it's not, A and B are not the max and the min. Okay. If x1 and x2 are not the inputs, then there exists either a maximum or a minimum value of f at C, which is inside of AB. So, by theorem 26.1, which we just covered, we have that f prime of C is equal to 0. And that's it. Therefore, there exists a point in, well, let's call it C. Point C in AB such that f prime of C equals 0. That's what we want to show. Okay, so if it's constant, we're good to go. If it's not constant, then it's a max or a min inside of an open interval where it's differentiable, and thus its derivative is 0. Any questions? So that's what we call Rolle's theorem. All right. And Rolle's theorem is kind of like a major lemma for the big event of this section, which is the mean value theorem. Okay. So let me erase and I'll write down the mean value theorem. Okay, so this is theorem 26.3. 26.3. It's kind of fun writing on these things while they're like swaying, by the way. The mean value. All right, let f be a continuous function on AB that is differentiable on the open interval from AB. Then there exists at least one point C in AB such that f prime of C is equal to f of B minus f of A over B minus A. All right, so what does the mean value theorem say? Let's draw a picture too, just to kind of see what's going on here. But you've seen this in calculus also. So we have a graph. Say we have two x values, A and B. F of A is something. What is f of A? F of B is something, probably something else, but not necessarily. F of B. And then there's some function, right? Maybe I'll draw it like this. And what the theorem says is that there's a slope between these 2 points. typically we would call that a secant line, okay? And the slope of that secant line is the rise over the run, right? So you could say that it's f of b minus f of a over b minus a, or this. So this is just the slope between the endpoints, right? And what this is saying is that somewhere in between a and b, the slope of the curve is equal to the slope of that secant line. And again, this is something we typically talk about in Calculus 1, although we may or may not really go through the proof. But so once you see the slope of that secant line, there should be some points in between a and b, one or more, where the slope of that curve is exactly the same. And I think if we're looking at this one, there's probably like 2 places, like somewhere in here and like somewhere around there are 2 places where the slope of the curve is equal to the slope of that secant line. And that's what the mean value theorem says, okay? Is that if you find the slope of a secant line, if this is a nice continuous function on the closed interval and it's differentiable on the open interval, then there's going to be some point in between a and b where the slope of the curve is equal to the slope of the secant line. That's a nice way to say it if you were just telling somebody. Okay, let's prove it. So proof. So the way that we prove the mean value theorem is we're going to make up a new theorem. Not a new theorem, a new function. So let's let g of x be equal to the following. I'm going to let it be f of b minus f of a over b minus a times x minus a plus f of a. Now, what can you tell me about this function g of x that I just wrote down? First of all, it looks bad, but what kind of a function is it? It's just a line. Does everybody agree with this? That g of x is just a line. Well, I think that you will believe me when I say that lines are continuous. And I think you'll also believe me when I say that lines are differentiable. I think you could even tell me what the derivative of this line is. Right, what is it? Yeah, it's f of b minus f of a over b minus a. Right, so this is just a line. So nothing super special here. So now let's, also what do I know about the function f of x? Well, f is continuous on this and it's differentiable on this. This one is continuous on the closed interval. In fact, it's continuous everywhere and it's differentiable everywhere, right? So now what I could do is I could say, now let's let h of x be a new function that is f of x minus g of x. Well, both of these are continuous, so their difference is continuous. Both of them are differentiable, so their difference is differentiable. So this function h of x is continuous on the closed interval and differentiable on the open interval. So it has all the properties that we like. Okay, so let's look at, consider h of a. Well, h of a is equal to f of a minus g of a. So I guess the question is, what's g of a? So look back up at g and tell me if I plugged in a for x, what would I get? F of a, because this thing would become 0. So that whole term is 0, and I'm just left with f of a. So I get f of a minus f of a, which is 0. Let's look at h of b. H of b is f of b minus g of b. Well, what's G of B? Let's see. So if I plug in B here, I get B minus A. That cancels this B minus A. So that's gone and that's gone. So I get F of B minus F of A plus F of A. The F of A's cancel, and I'm just left with F of B minus F of B, which is 0. Okay, this is kind of special because I have that at A and at B, H is 0. So it fits the conditions of Rolle's theorem. And Rolle's theorem says if you have two endpoints that are equal, then somewhere in between, what happens? The derivative of H is 0. Agreed? So what I know is, so by Rolle's theorem, there exists C in between A and B such that H prime of C is 0. Okay, well that seems good. What is H prime of C? Yeah, so we already know what H of X is. It's F of X minus G of X. So that means that H prime of X is just F prime of X minus G prime of X, correct? So if I wanted to know what is H prime of C, well, H prime of C would be F prime of C minus, well, G prime of C. What's G prime of X even? Well, we kind of just already said that, right? Because I asked you, what's the derivative of this thing, right? And what was it? What's the, oh, okay, so if I go back over here and I just ask you, what's, I'll write down here, G prime of X.
F of B minus F of A of B minus A.
Yeah, it's just the slope, right? So it's F of B minus F of A over B minus A. F of B minus F of A over B minus A, right? So what's G prime of C? Yeah, same thing, it's constant, right? The derivative is constant. So G prime of C is just F of B minus F of A over B minus A. But I said that H prime of C is equal to 0. So now I could just move this thing to the other side and I get that. So F prime of C is equal to F of B minus F of A over B minus A for some C in AB. And that's what we wanted to show. So that's the proof of the mean value theorem. And that's actually super, super important when we get into integration. Like, we actually can't prove certain things about integration without the mean value theorem. In fact, that's like the Riemann integral depends on the mean value theorem. So we need this very bad. So this is a big proof in some ways, even though like when you just see the result, it's like, okay, so there's a secant line and somewhere in between the slope is equal to the secant line. It seems like, okay, not super helpful, but I guess it's true. It's like, no, it's actually super, super, super helpful that that is true. Any questions on this proof? All right, I have 10 minutes. Let me see what kind of proof. Oh yeah, we can do this one. So next theorem is theorem 26.6. And it says let F be continuous on closed interval AB and differentiable on the open interval AB if f prime of x is equal to 0 for all x in AB, then f is constant on the closed interval from A to B. Okay, and so this is kind of leading us to some of the places that we'd eventually like to go, and that is if I say that you have a function and its derivative is constantly 0, then I can say that f is a constant function. Yeah.
Did we like assume this to just prove one of the other theorems?
No.
Or did we
What I did is I said that if you have a constant function, its derivative is 0.
Oh, so we're going to.
Yeah, what this is saying is if something's derivative is 0, it's a constant function. Now, that's not obvious, right? Because we know that there are functions that have the same derivative. Like we'll take x squared and x squared plus 2. Now they have a constant difference, right? But certainly they have the same derivative, 2x, right? So what I always think about is like, well, couldn't there be some like just wild, crazy function I could make? Maybe it takes like 14 pages to write the function, but it just magically its derivative is 0. And what this theorem says is, no, that's impossible. You can't have some really wild function where its derivative is identically 0. The only way that can happen is if the function is constant. Make sense? Okay, so that's what this theorem is saying is if you see that something has a 0 derivative constantly, then that function must be constant. Let's prove it. So proof. We'll suppose not. Okay. In other words, let's suppose that we do have a 0 derivative, but the function itself is not constant. So f is not constant on AB. So that would mean that there exists a maximum and a minimum on that interval. Right? We're on a closed interval and it's continuous differentiable. So we have an absolute max and an absolute min. So there exists x1 and x2 in AB such that A is less than or equal to x1 is less than or equal to x2 is less than or equal to B such that f of x1 is not the same as f of x2. Now, this doesn't even have to be a maximum and a minimum, actually. I use it because I know it has such things. But what I really could just say is like, if it's not constant, then it has 2 points that don't have the same functional value. That works. So I don't even need those to be the absolute max or the absolute min. Any 2 points will do. So I just take any 2 points and say they don't have the same functional value. Okay. So there exists C in x1 to x2 such that f prime of c is equal to f of x2 minus f of x1 over x2 minus x1. So I just said, hey, everything is satisfied for the mean value theorem. So I could use the mean value theorem on x1 and x2, where I know that f of x1 and f of x2 are not the same. So what I get here is that certainly x2 minus x1, they're different points. So the bottom is non-zero. The top, these are different functional values. So the top is non-zero. So non-zero divided by non-zero is non-zero. So this thing is not zero, but that's a contradiction because I just found a point in between A and B where the derivative is not equal to zero. And I said that the derivative is identically zero. So that's a contradiction. We know that f prime of x is zero. And so therefore, I can say that f is constant on the closed interval from A. We're done. I think I wrote one thing wrong. Yep. That's not equal to. Any questions? Okay, so this one is typically in calculus called the zero derivative theorem. That because if your derivative is zero, then you have to be a constant. Okay, that's it for today. We'll pick up where we left off on Wednesday. I do need to collect some homework, so you can just turn it all in to me, paper clipped, before you go. Have a good day.
Does anyone need that to produce a book? All good. We got to put the full.